Okay, so I think we can start. There was a long break, at least in the lectures. So to quickly review, we were talking about Bayesian linear regression. We completed the part where sigma square was known, but that is not a realistic scenario. And now we were discussing, or we started discussing at least the scenario where sigma square will be unknown, or more realistic scenario, right? And we did start discussing about it, but we did not complete it. So to quickly review what we did or what we discussed on this was that the likelihood will take the following form, the first equation from the last lecture, which is basically nothing but the same likelihood as the case when sigma square was known. So the likelihood does not change whether sigma square is known or sigma square is unknown. So the likelihood remains as it is, and that is the first equation. And then in the second, I said that when sigma square is unknown, my conjugate prior will be Gauss inverse gamma, and the Gauss inverse gamma takes the form that is shown here. And practically this is where we stopped, because we started actually, but we did not complete computing the posterior. Okay. So let us start with computing the posterior, because that is where we left last time. Okay, so this is the first expression is the likelihood, the second expression is the prior. Okay. So we want to compute the posterior distribution, which is probability of the things that I want to infer, which in this case are weights W and the sigma square, because both are unknown. And the Bayesian way of doing things is that whatever is unknown is uncertain, whatever is unknown is to be treated in a probabilistic sense, and whatever is unknown is to be inferred by using the Bayes law. Okay. So the posterior distribution I want to compute is basically W comma sigma square given data. Okay, that is what we want to compute. So using Bayes law, probability of sigma square given data is proportional to probability of W comma sigma square multiplied by probability of data given W comma sigma square. This is my prior and this is my likelihood or data likelihood. Okay, right? And now from the previous slide or what we did last time, probability of data given W comma sigma square is nothing but probability of P, which is my target, given X, which is my input, comma W comma sigma square, which is nothing but a Gaussian, over T given phi W comma sigma square I. Right? This we had done last time, nothing new. The same thing written in a compressed form, which is proportional to sigma square to the power minus n by 2 exponential of minus 1 by 2 sigma square phi W minus T transpose phi W minus T. Okay. So this is basically the PDF expression of the multivariate Gaussian, and it's proportional because I'm not writing the normalizing constant, at least the total normalizing constant. I'm only writing the determinant of sigma part, and that gives sigma square to the power minus n by 2. N here is the number of training data I have, so that's why the minus n by 2 is coming into picture, right? So this is nothing new. This is actually what we have already done. And so therefore, probability of t given x comma w comma sigma square is proportional to, what I will do is that you see that transpose term, that is like a square. So I will open that up and write it down in a simplified form. Is proportional to sigma square to the power minus n by 2, right, exponential of minus 1 by 2 sigma square, and then you have, what do you have? Yeah, W transpose phi transpose phi W minus 2 W transpose phi transpose T plus, I think, T transpose T, yeah, T transpose T. Okay. I have just opened up the bracket and it's like a square minus 2ab plus b square. You can think of it in that manner. Just it's vector and matrices, so I cannot write square. I have to write transpose in the transpose form, right? And this is nothing new, by the way. This we did already last time. I'm just repeating it because there is a long break, so I'm repeating that portion. Okay. Okay. Let us go to the prior part. Prior was probability of W comma sigma square. It was Gauss inverse gamma of W comma sigma square given W naught comma V naught comma A naught comma B naught, which is proportional to Gauss times inverse gamma. Gauss is for weights, inverse gamma is for sigma square. So this is Gauss, okay, not proportional to, if I am writing in this manner. If I am writing in this manner, it is actually equal to Gauss W given W naught comma sigma square V naught inverse gamma sigma square given A naught comma B naught, which is proportional to the Gaussian part. If I write, it will give me sigma square. So what is the dimension of W? W is a vector, weights, right? So as per our notation, it was k plus 1, because I start from 0 and go up to k. I use k plus 1 basis function. So the dimension of W is k plus 1 and we called it k prime. Okay. Sigma square to the power minus k plus 1 by 2, which is k prime by 2. So I will directly write k prime by 2, exponential minus 1 by 2 sigma square, and then what do you have? W minus W naught transpose V naught inverse W minus W naught. This is the Gaussian part multiplied by the inverse gamma part. And inverse gamma, the PDF is equal to sigma square to the power minus in bracket A naught plus 1 exponential minus B by or B naught by sigma square. So the other part is, this is corresponding to the inverse gamma part, sigma square to the power minus A naught plus 1 exponential of minus B naught by sigma square, not sigma 2. Okay. So this corresponds to the inverse gamma and this corresponds to the Gaussian, and that's why the total thing is Gauss inverse gamma when you do the product. Okay. Okay, so now let us start computing the posterior, and that is where we stop. So now let's call it equation 3, let's call it equation 2, not this one is equation 2, and we want to substitute equation 1 and 2 and 3 into equation 1. Okay, so substituting equation 2 and equation 3 into the Bayes law. Okay, so substituting equations 2 and 3 in equation 1. What do we get? We get, and this is the part you need to be careful about. I am computing probably this one. This is proportional to, see, there is sigma square to the power minus k prime by 2, which I will keep as it is. Okay. So the first term I am taking is sigma square to the power minus k prime by 2, which I will not touch. Then there is sigma square to the power minus a naught plus 1 and sigma square to the power minus n by 2, right? Sigma square to the power minus a naught plus 1 in equation 3 and sigma square to the power minus n by 2. I will combine this. Okay. So I am basically combining sigma square to the power minus n by 2 along with sigma square to the power minus a naught plus 1. This two part I am combining, and that will give me sigma square to the power minus a naught plus n by 2 plus 1. Okay, clear what I have done? And then what is remaining? See, there are two exponentials remaining here. In equation 3, there are two exponential which I have to accommodate, and there is one exponential in equation 2. I will put all of this exponential together. So everything will come together. Okay. So now, along with that, I have exponential, and one thing that you will observe is that in all of this exponential there is minus 1 by sigma square that is present. Minus 1 by sigma square, minus 1 by 2 sigma square, and minus 1 by 2 sigma square. So this minus 1 by 2 sigma square I will take outside and keep it as it is. B naught will become 2 B naught, that's simple. So minus 1 by 2 sigma square I keep as it is. Now let us see. Let us go to this term. Okay, and here I have already opened the bracket, and first we are interested in the quadratic terms, quadratic in W. So one term I can see here is this one. So I will take this term. Along with that, I will get a quadratic term by opening up this bracket, right? These two terms we are going to write first. So what will it be like? The first term is W transpose phi transpose phi. So phi transpose phi. Okay. W I will write later. So that is this portion, and from here what will I get? V naught inverse, because W transpose V naught inverse W I will get. So V naught inverse is there. So plus V naught inverse W. Okay. So this V naught inverse is coming from the prior equation 3. Phi transpose phi is coming from the likelihood, equation number 2. And obviously phi is function of your training data, so that has to be likelihood. And V naught is your prior parameter, so that has to be prior. Okay. So that was my quadratic term. Next, what will I take? The linear in W. So minus, and there will be a 2, so minus 2 W transpose. Okay, let me change the color actually. So minus 2 W transpose, and in the bracket what will I have? Let us see. Let us go here. So this one is simple. I will have P transpose T. That is the linear term, right? P transpose T in equation 2. This term basically. So P transpose T, and if you go here, what will you have? W transpose, then V naught inverse W naught, and that will come 2 times because once from left and right, so 2AB in that form. So plus V naught inverse W naught. Okay. And now what I will do is I will write everything that is remaining. Every other term that is remaining, I will now write it down. Okay. So basically, apart from the linear term and the quadratic term, whatever is remaining. So that let me write down in another color then. This is okay. So let us see. So what is remaining from here? What is the remaining term? T transpose T. So let us write it down. T transpose T. And what are the remaining terms from here? W transpose V naught inverse W naught. That is one term. So W naught transpose V naught inverse W naught. Transpose V naught inverse W naught. Plus, is there anything else remaining? 2 B naught from the bottom one. This B naught will become 2 B naught because I have written 2 sigma square. So plus 2 B naught. Close the bracket, close the bracket. Clear what I have done? Clear? So now remember that I am computing the posterior, right? Which means if it is really a conjugate prior, then my posteriors would be following what distribution? Gauss inverse gamma. So the posterior forms would look like equation 3, right? Which means there should be a Gaussian component and an inverse gamma component, right? And the inverse gamma component will be only over sigma square. So whatever W term is there should be in the Gaussian component. Clear? I am repeating. So since I am using conjugate prior, my prior and posterior should follow the same distribution. So if my prior is Gauss inverse gamma, my posterior should also be Gauss inverse gamma. And not only that, the inverse gamma is over the sigma square. So the inverse gamma should be over sigma square only. Whereas the Gauss component is over the weights. So all the W terms would come under the Gaussian component. Okay. So we will do a small trick. Let us see what we will do. So let us introduce some variables actually. So see this variable. This I can call as, any idea what will I call it? Vn, because in the Gaussian component in between the V naught was there. In the Gaussian component in between there is V naught inverse. After you have observed the data, V naught should become Vn. So the prior variance should become posterior variance. So this one I will call Vn inverse. So suppose Vn inverse is equal to P transpose phi plus V naught inverse. Clear? What I have done? Basically, just given some name. Now, second thing, you tell me, what is the term that is with the linear W transpose? Phi transpose T plus V naught inverse W naught. I want to give another name for that. What should I give? If you want to, the clue, let me give you a clue. The clue is that, think of Gaussian. In Gaussian, what is there with W transpose? The linear term. Look at this top expression and tell me, what is there with W transpose? V naught inverse, W naught. So now if it is going to be the posterior, I should call it Vn inverse Wn. Just comparison, nothing else. Okay. So and we also introduce, take this term, this whole term, and we call it Vn inverse Wn is equal to P transpose T plus V naught inverse W naught. Clear why am I doing this? Just to bring the posterior as the same form as the prior, nothing else. Now with this notation, I will now write it down. So therefore, probability of W comma sigma square given data is proportional to sigma square to the power minus k dash by 2 sigma square to the power, another name I did not give, a naught plus n by 2 plus 1. Compare it with this one and tell me what a naught plus n by 2, what should I call it? Last time also I told it. A naught plus n by 2 will be called an. So the total thing will become an plus 1. An plus 1, and that is happening because this one I am calling an. Okay. And then exponential minus 1 by 2 sigma square. What do I have? W transpose Vn inverse W. This is our notation, right? Vn is what we have introduced, plus or minus, sorry, minus 2 W transpose, and then what did I call it? Vn inverse Wn. Inverse Wn. Okay. So now I want to complete the square. So what is the term that is missing? A minus b whole square. Think about that. I have a square and I have a minus 2ab. The b square is remaining. So b square is what? Wn transpose Vn inverse Wn. So if you go here, W naught transpose V naught inverse W naught, that will become Wn inverse Wn transpose Vn inverse Wn. So basically I want to complete the square. So therefore I will myself add it, Vn inverse Wn, and then I have to subtract it also. I just cannot randomly go on adding things. Okay, I added it and subtracted it. And then the remaining terms, whatever they were, I will write it down. So what were the remaining terms? Plus, there was T transpose T, I remember. Plus, I remember there was W naught transpose V naught inverse W naught plus 2V naught. If I am not wrong, these are the terms that were there. Right? Yeah. So the last three terms. Any doubt until now? Okay. Lot of mathematical operations, but not very difficult. Obviously, I have again repeated it in the homework, so you will anyways have to do it, and that time any doubt will be clarified. Okay. So this exact question has been given in homework 1. Okay. So now this is then equal to sigma square to the power minus k dash by 2 sigma square to the power minus a n plus 1 exponential minus 1 by 2 sigma square. And now tell me the first three term, if I combine them, how can I write it? The first three term. Can I write it as, how can I write it? W minus Wn transpose, Vn inverse, W minus Wn. The Gaussian part is now there. So this should be W minus Wn transpose Vn inverse W minus Wn. Okay. So now go back, or let me close the bracket now. Okay. And whatever is remaining, that I will keep it as a separate exponential. Whatever is remaining. So whatever is remaining is exponential minus 1 by 2 sigma square. I am still keeping the 1 by 2. And what is remaining? Minus Wn transpose Vn inverse Wn plus T transpose T plus W naught transpose V naught inverse W naught plus 2 V naught. So starting from the fourth term, everything is remaining. And what is speciality about this term? Can you tell me? This term has any speciality? Can you have some observation about this term? Anything? There is no W here. There is Wn, which is constant, a parameter, but there is no W. W is not there because that was supposed, no, that is sigma square. So V naught is there, so it should be function of sigma square actually. 1 by sigma square is there outside. So there is sigma square, but there is no W. And remember what I said? I want to separate it out so that there will be a Gaussian term involving only the weights and sigma square. And there should be an inverse gamma term which should be involving only sigma square. So this exponential is going to be corresponding to the inverse gamma. So that means from here I should get my Bn, because B naught is to be updated to Bn and that is still pending. That I should get from here. Where was I? Yeah. Plus. Yeah. This is Vn, right? Yeah. Plus T transpose T plus 2 V naught. Okay. Clear? Whatever was remaining, I have just written it down, nothing difficult. So now, last thing, I am going to take this term and this term and write them together. So what does it look like if I combine those? Can I say that it is a Gaussian? It's a Gaussian, right? So this is equal to a Gaussian of W given Wn comma sigma square Vn, and Wn and Vn I have already defined. Where? Here. Those things are already defined here, Wn and Vn. Okay. What is the remaining term? The remaining term is this one and this one, and that should give me the inverse gamma. So let me directly write it down as inverse gamma, and then we will figure out what is An. An I have already defined. What I have not defined is Bn. Okay. So now you tell me what is Bn, and I will take you to this slide and tell me what is Bn. What is Bn? Okay. And you will need, I think, this one also. So look at B naught and the inverse gamma expression. Okay. So sigma square to the power divided by 2. So the whole thing that you see inside the bracket divided by 2 is your Bn, because then only it will become Bn by sigma square, right? So therefore Bn is equal to B naught plus half W naught transpose V naught inverse W naught minus Wn transpose Vn inverse Wn plus T transpose T. Okay. So that means your posterior distribution is Gauss inverse gamma with posterior weights, I mean the mean of the posterior weights as Wn. Okay. The variance Vn is equal to posterior variance, I mean sigma square Vn is the variance anyways. An is the posterior parameter of the inverse gamma. Bn is the posterior parameter of the inverse gamma also. So let me write it down the other things also, not only Bn. An, what is An? Remind me. A naught plus n by 2. What is Wn? We will write later. First let me tell what is Vn inverse. V naught inverse plus phi transpose phi. Okay. And lastly, what is my Wn? This is equal to Vn multiplied by V naught inverse W naught plus phi transpose T. So all of this is coming, two things are coming from here. I am just taking Vn to the right hand side, the last line you see, and An is coming from the top and Bn is coming by comparison. Okay. So now imagine you have to write a code, you have to write an algorithm. Let us imagine that you have to write an algorithm. What do you need for writing a code? All this derivation you will do on paper, and let's say that is done. Once the derivation is done and I want to write a code to find out the posterior weights and posterior sigma square, what will my algorithm look like? You will have data D. From there you can calculate the number of data points. Okay. You can calculate phi, capital phi, and T is given to you. Now once these things are given to you, the first thing will be An is equal to A naught plus n by 2. Done. One line. Second will be Vn inverse is equal to V naught inverse, which is given to you because it's prior, plus phi transpose phi. Done. Third will be Wn is equal to Vn plus V naught inverse W naught plus phi transpose T. Done. Last will be Bn. Then again everything is known, you see. And once these four are done, your posterior is done. So the algorithm, the code part is very simple. The derivation part is the one that is correct. So the algorithm, for inferring the posterior. Okay. So first, what is your input? Let us see. Your input is D, which is xi comma ti, I equal to 1 to n. So your training data is given to you. It has to be, otherwise what are we learning? Right? Second, you also have to give your prior parameters. So W naught, V naught, A naught, and B naught are known to you. Right? These are the things known to you. Step 1 is you will calculate phi, and phi is basically how will it look? Phi 0 x 1 phi 1 x 1 phi k x1. This is the first row where you are taking the first training sample and all the basis functions are evaluated, right? The second row will be, can you tell me the first element of second row? Phi naught x2. Phi naught x2. Obviously, the basis function you have selected, so that is also known to you. Remember that. For example, it can be x, x square, x cube, something like that if you choose that. x2 phi k x2. Not write the others, but you know the last one will be phi naught xn phi 1 xn phi k xn. So you can compute phi. That's the point. And what is the name of the phi? Remind me. Design matrix. Okay. Phi is known as the design matrix. That's the name. So that is step 1. Step 2, obviously T vector is also known to you. That is T1, T2, T3. That is also known to you. Step 2, your AN you will set it equal to A naught plus N by 2. Okay. That is your step 2. Step 3, Vn inverse, you will set it as V naught inverse plus phi, which you have already computed, transpose phi. Okay, and from there you can invert it to find out Vn if you want it. That's trivial. Fourth is Wn, and that will be equal to Vn, which you just calculated, multiplied by V naught inverse, which is known to you, that is the input, that is the prior parameter, W naught plus phi transpose, you have already calculated, T already known to you because that is, those are the Ti's written in vector form. So T is nothing but T1, T2 dot Tn. So known to you in vector form. Okay. And last but not the least, Bn will be equal to B naught plus 1 by 2 W naught transpose known to you, V naught inverse known to you, W naught known to you, minus Wn transpose you have just computed, Vn inverse you have already computed, Wn you have already computed, plus T transpose T known to you. That's all, right? B naught is outside. And that's it. And you will return these 4 quantities. So the algorithm is as simple as it can get. There is no for loop, nothing is there. Okay. But to use this algorithm, first you have to do the derivation. Okay. So that is how Bayesian and probabilistic machine learning works. First you do the derivation, then you write the algorithm. And once you can write that, it will realize that in most cases it is 3, 4, 5 lines that is coming. It is generally not difficult. Clear? But now, what is our objective in machine learning in general? To predict. What we have done is not predict. This is equivalent to training. But now I want to make predictions. And in Bayesian, how do we predict? We compute the predictive distribution. Okay. So let us go there then. So the algorithm ends here. Obviously, you can write a return statement. I am not writing, but you can write. Okay. To be more formal. Okay. For predicting, we have to compute the predictive distribution which takes the form probability. You want to find T star, which is unknown. you want to find a distribution for T star. Given X star, which is a new input. So at a new X, you want to find or predict T. But in this case, since it is Bayesian, you want to find a distribution, not a point estimate. Comma X comma T, and this is my training data. So this is what we have to compute, right? And we have already computed it for the case where sigma square was known or beta inverse was known. Last class we did it. So now we have to extend it for the case where sigma square / beta inverse is unknown. Okay. So tell me, how can I compute it, or remind me rather. T star given X star comma D. How should I write it? What is it equal to from last lecture? Remember, you have computed the posterior distribution. So you have to use the posterior distribution along with the likelihood. So this is equal to, I will use the sum and product law. Those are the only laws I know. Those are the only laws we use here. This is equal to integration probability of T star given X star comma W comma sigma square. So once I condition on W and sigma square, I need not write data there because they are conditionally independent. If I know W and sigma square, given X star, I can find out T star. If I know W and sigma square. So whether I know the data or not does not matter. That is one way of understanding this. The other way of understanding is that whatever information data had is now encompassed in your W and sigma square. So that information is already encompassed, so you will not get any new information by writing D there. Okay. So given W and sigma square, whether you know D, you do not know D, that is immaterial, that is conditionally independent. Okay. So this is your likelihood multiplied by the posterior, and then what will you do? This is the product law I have used. I have written an integration also, but integration over what? In the previous case, we integrated over W. It was a Gaussian convolution of Gaussians is Gaussians. That's what we wrote, right? In this case, what will be? W and sigma square, because previously your posterior was over W. Now your posterior is over W and sigma square. So both of those you have to integrate out. Another way of understanding is that on the left hand side, do you see W and sigma square? So whatever is not there on the left hand side has to be integrated out. So dW d sigma square, so there should be another integration. Okay, one for W, one. So can you tell me how many integration actually are there? I have written 2, but actually how many integrations are there? How many? K plus 2. K plus 1 is weights and 1 sigma square. So actually that is equivalent to K plus 2 integration. I have written the K plus 1 W's as a single integral, but that's a K plus 1 dimensional integral, and sigma square as a single integral. So overall it is K plus 2 integral, which I have written as K2 integral. Clear? Now tell me, what will be this equal to distribution wise? What will this be equal to? What will be this distribution? You know this. This is the likelihood. So what is the distribution of the likelihood? Let me help you a little bit. Remember, T is equal to W transpose phi x plus epsilon, where epsilon was from Gaussian 0 comma sigma square. So now tell me, what will be this distribution? Gaussian with mean phi x star transpose W, or W transpose phi x star, whatever you want to write, and variance sigma square. Clear? Always whenever you have doubt, go back to the original where you started. Always go back to the basics, and the basics is that we were solving linear regression. This is the linear regression. So go back there, you will get your answer. So this is actually, as you correctly said, Gaussian over T star given phi of x star transpose W comma sigma square. Okay. So I will delete the bottom portion. That was only for your understanding. And tell me what is the other distribution? What is this? This Gauss inverse gamma. So this is Gauss, I will write separately, or okay, let's write Gauss inverse gamma, I will write separately later. W comma sigma square given Wn, Vn, An, Bn. And this is the integration we need to, or we want to solve. Okay. So let us substitute now whatever we know, and let's see if we can solve it. Actually, this is another homework, so I will not solve it actually, I will only give you the answer. So this is equal to integration Gaussian T star given P of x star transpose W comma sigma square, and then Gauss inverse gamma is equal to Gauss times gamma, Gauss W given Wn comma sigma square Bn multiplied by inverse gamma of sigma square given An comma Bn dW d sigma square. Clear? Is it clear? So now let us make some observations. Inverse gamma do not have any W. So that means when I do a integration over W, that term will be like a constant, but W has sigma square. So that means first I have to integrate out W, and only then I can integrate out sigma square. So the inner integration should be of W, the outer should be of sigma square, but inverse gamma should be only there in the sigma square one. Clear what I said? Let me write it down. So this is over the sigma square, okay, and then let us write over the W1. Gauss T star given P of x star transpose W comma sigma square multiplied by Gauss W given Wn comma sigma square Vn dW. So this one ends, and then there comes a inverse gamma. So inverse gamma sigma square given An comma Bn d sigma square. Okay. D sigma square. I think there should have been another bracket here. Okay, and that bracket ends here. Okay, or rather, let me end it. Okay, clear? Look into this expression carefully and let me know if it is clear or not. It's not difficult. What I have done is that there are two integrations, the 1 over W, 1 over sigma square. Inverse gamma do not have any W, so that will only appear when I do a integration over sigma square, so that is outside the bracket. Everything else is the integration should be inside both the integrals, so that is the inner integral, correct? Clear? Now tell me, what is that inner integral? The black one, black integral you see over dW, what is that equal to? the black integral, ignore the red part, the black integral, which is the integral over dw, can you, without even integrating, can you tell me what will be that distribution equal to? There are two integrals. One is the outer integral, one is the inner integral. What is the inner integral? The inner integral is Gaussian over t star multiplied by Gaussian over w dw. This integral, what is the outcome of that? What will be the result? Gaussian. Why? What theorem? Convolution of Gaussian, it will be equal to Gaussian. So this part, as you see, will yield you a Gaussian. Tell me what will be the Gaussian equal to? This is exactly same as sigma square known. So what will be the Gaussian equal to? What will be the mean? So the mean will be phi x transpose Wn, correct? What will be the variance? Sigma square plus, repeat. There is no sigma square plus Vn plus 1. क्या पूछ रहा हूँ? I am asking the inner, the red second bracket, the curly bracket you can see. I am asking what will be the output of that curly bracket. That's all. So what will it be? So all of you said that it will be Gaussian because it's a convolution of Gaussian. I agree. So if it is a Gaussian, then you have to give me the mean and variance. So what is the mean? And the answer was correct, that phi x star transpose Wn. W will be replaced by Wn. What is the variance? A variance of x, A transpose plus L inverse, you remember something like that? So what will it be? Put it and tell me. So what is A here? What is A? Phi x star transpose is your A. So then what will be this thing? It will be A, which is phi x star transpose, multiplied by sigma square Vn. Sigma square Vn multiplied by A transpose, which is phi x star, plus sigma square. So let me write it down. So this is equal to integration, the inner will become Gaussian over T star given phi of x star transpose Wn, comma phi of x star transpose sigma square Vn phi of x star plus sigma square. This is the inner integration. And what is remaining? Inverse gamma. So that should also be there now. In inverse gamma, sigma square given An comma Bn d sigma square. Look into it very carefully and ask if there is any doubt. That how did we arrive at this? Any doubt? Ask now or ask later. Yeah. Okay. So last time, let us go back to the last class thing. So last time we were saying that suppose there is y given x is a Gaussian over y given ax plus b, where A is a matrix, x is a vector, b is a vector. And we also said that, let's say, okay, there has to be a variance also, L inverse, let's say. And then x given mu comma sigma inverse. Okay. If that is the case, then we showed last time that probability of y will be equal to Gaussian over y, a, x will become mu of x, or expectation of x, which will be mu, plus b, comma, now the covariance part. So covariance of this will become a covariance of x, a transpose, a covariance of x, a transpose, which is equal to a sigma inverse a transpose plus L inverse. Now how did we arrive at this? So this is what we have used. Okay. Now how do we arrive at this? Just to remind you. So I said that y is equal to a x plus b plus epsilon, where epsilon is actually Gaussian with 0 comma L inverse, right? Yeah. Okay. Then tell me what is probability of y given x? What is this equal to? What is this equal to? Normal of x, y. What is this equal to? Normal of y given ax plus b, because that becomes constant, so that is my mean. And what is the variance? L inverse. So this expression is equivalent to this expression, which is the exact expression that I had here. Correct? So now from this expression, take mean of both sides. So what is the expectation of y? What is expectation of y? What is the expectation? The basic rule of expectation. What is it? A, then expectation of x plus b plus 0. So that will give you a expectation of x plus b plus expectation of epsilon, which is equal to a expectation of x, let us call it mu, so a mu plus b. Clear? And that is what I have written here, a mu plus b. Okay. Now what will be the covariance or covariance matrix of, or covariance of y? Covariance of y will be equal to a covariance of x, a transpose, a covariance of x, a transpose. What is covariance of a constant? 0. So that will become 0. And what is covariance of epsilon? L inverse. So then this is equal to a covariance of x is equal to, let's what I have taken, sigma in, I think lambda inverse, right? Okay, there is a notational mistake here. We should call it lambda inverse, because sigma is for, yeah, I mean you can write sigma, there is nothing wrong there, but then sigma is your precision, not your covariance. So lambda inverse A transpose plus L inverse. This we did last time. Okay, same thing. Same thing when you apply, you get what I have written there. So I'll ask again. Now can you relate to it? What I have done? A is nothing but phi x transpose. That's all. B is equal to 0. lambda inverse is equal to Vn, and your L inverse is equal to sigma square. Not sigma square, yeah, sigma square Vn, right? Any doubt? But still there is one integral that I have to find out. So what will be that integral equal to? What do you have? Look at the integral very carefully and tell me what do you have. You have a Gaussian multiplied by the inverse gamma, where inverse gamma is controlling the variance of the Gaussian, and then you are integrating over inverse gamma, sigma square. So think about it, what do you have? You have something like a Gaussian over, let's say, x mu comma sigma square, and then inverse gamma is over the sigma square with some parameter a comma b, and then you are saying that you will integrate out sigma square. This is the form you have. Are you able to relate? This is the exact form that you have here. I have just simplified it. So what will this integral be equal to? That I will not do it, that's a homework, but I will give you a clue. Okay. So this is like saying, if I write it in summation form, what is it like saying? It is like that I have many summation over Gaussians, infinite summation over Gaussian, because integration, where the variance of the Gaussian is coming from a inverse gamma distribution. So it is like saying this is equivalent to summation over Gaussian or sigma square, where sigma square is coming from some inverse gamma distribution. Are you able to relate these two things? Okay. Can you write integration as a summation, practical 0? How do you do that? How do you write integration as a summation? By converting it to a expectation. You write an integration as a summation by first converting it into an expectation and then using sampling. So tell me, is it not equal to expectation with respect to inverse gamma of the Gaussian? You can write expectation of the inverse gamma with respect to Gaussian. That's also fine. Is it not? Now, if it is expectation, so then how can I do it? I should draw sample. Sample from where? From inverse gamma. And for each of those samples, I should evaluate what is inside. So isn't that equal to what I have written earlier? And how long should this summation go? Infinite. Because law of large number, or whenever you are trying to approximate a integration by a summation, then you will get the exact result when the number is very large. And you saw it while computing pi in your home practical 0. You are only getting the correct pi when you were taking 10 to the 7 or 10 to the 8. You are not getting for 10,000. Why were you not getting? Because you will only get the exact number when the number of samples become very high. And this is from practical 0, you have done it. Okay. So that means this summation ideally should go up to as high as possible, theoretically infinite. Correct? So that means, what is this distribution equal to now? What is this distribution equal to? Infinite mixture of Gaussians. What is mixture of Gaussian? Mixture of conjugate prior beta we did. It was two beta distributions weighted by something. In this case, there are infinite number of Gaussian distributions. What? Okay, not relevant, but anyways. So yeah, this is infinite mixture of Gaussian, and you have to prove that infinite mixture of Gaussian gives you student state distribution. That is your homework one of the problem. Okay. So Just to conclude things, let us call it what? Equation 4, I guess. So, equation 4 is infinite mixture of Gaussians with the covariance of the Gaussian drawn from inverse gamma. Okay, and this yields a students T distribution. Okay, this yields a students T distribution, and I will give you the answer also. So, integration of Gaussian W or x, I think, x given mu comma sigma square multiplied by inverse gamma sigma square given a comma b. If you do this, you will get a students distribution, and this you have to prove, of x given mu, which is the mean, remains as it is, comma b by a sigma square to the power minus 1 comma 2a. So, students distribution has how many parameters? 3. The first parameter is the mean. The second parameter is known as precision. So, this is the precision of students distribution. The third parameter is known as the degree of freedom. So, students distribution has 3 parameters: the mean, the precision, and the degree of freedom. And when you do a infinite mixture of, and student distribution is an infinite mixture of Gaussian, where the variance of the Gaussian are drawn from inverse gamma. That is the statement which you have to prove.
So we are mentioning sigma square is your distributions.
Then it will not happen. It will only happen when it is drawn from sigma square. Okay, I mean inverse gamma, or when beta is drawn from gamma. Beta is sigma square inverse. Okay. So let me summarize, because we are done with the Bayesian linear regression at least. So see, first is that when sigma square is also unknown in Bayesian linear regression, then a conjugate prior is a Gauss inverse gamma. Okay, when sigma square is unknown. Clear? And in that case, my posterior will also be Gauss inverse gamma, because that's a conjugate prior, and my predictive distribution will be students distribution. Okay. Now you have to prove that how the students distribution comes into picture, and not in this context. You can just take this expression and prove the one I wrote. Okay, that is what you have to prove, and then you have to work with both W and sigma square together. So when you are predicting, you have to integrate out both. It's not that you will only integrate W. Okay. To just conclude, and I have some time actually, let us write this one, equation 4. Let us write it down as students distribution, and you tell me what will I get. So simplifying equation 4, you tell me what will I get. Probability of T star given x star comma training data is a students distribution that I have already told you, T star. Now tell me what is the first term. I have given you the formula, just put it. What is the first term? Phi x star transpose W or W transpose phi x star? So phi x star transpose W. What is the second term? What is the second term? By looking at the expression I just gave here, Bn by An, and then Bn by An. Actually, this sigma square should not have been there. I mean, okay, let me write like this, that will help. Okay, here. Okay, let's write it sigma square V, and then this should be V actually. Okay, now it will be easier for you. So now tell me. So instead of sigma square, I wrote sigma square V because you have that form, right? So that's why. So to just be consistent with the form we have. So then, what is the second term? The precision will be equal to Bn by An, that is correct, and then look carefully.
Identity plus
Correct.
y extra transpose Bn phi extra.
Correct. Bn by An. It can be identity if you are trying to predict multiple, otherwise it will be 1. 1 plus phi transpose phi x star. What was it? I forgot. Let me see. Here it is, right? So it will be 1 will come from here. From here you will get a 1, and then phi x star transpose Vn phi x star. Transpose Vn phi x star. Whole inverse. And what is the third one? 2an. Third one is easy actually. Let us look into the second one again. Okay. See, sigma square is here and sigma square is here. So you take sigma square common. If you take sigma square common, what will you get? Second term will give you 1, right? Because it is, and the first term will give you phi x star transpose Vn phi x star. So this term is basically nothing but sigma square 1 plus phi x star transpose Vn phi x star, right? So that is coming here. That is coming here. That is that term. Sigma square you are integrating out. Remember, sigma square you are integrating out. So that's why sigma square is not there. Okay. So now what is the second term? Precision. Precision is related to predictive variance or predictive uncertainty. Now what is the uncertainty dependent on now? Look at that term and tell me. Forget about Bn by An for now, but or even consider Bn and An and then tell me. What is the uncertainty now dependent on in your predictive distribution? Your uncertainty has two components. One component is Bn by An, and Bn and An are the parameters of the sigma square, and sigma square is your process noise or the data noise. So one term here, so if you take the precision, you have Bn by An inverse, this is one term you will get, one term, and plus you will get Bn, okay, I think the bracket is wrong, it should be here, okay, plus Bn by A, wait, let me write it carefully, see. So now the first term is giving you Bn by An, and the second term is given you Bn by An phi x star transpose Vn phi x star, right? And then inverse of that, the whole thing, correct? Now think carefully, what is this first term denoting? This is uncertainty in your prediction because of your data is noisy. So this is because there is nothing to do with your amount of data. So the first Bn by An is denoting uncertainty in your data because your data is, because of your basically uncertainty because of noise in your data. What is the second term denoting? Uncertainty because of your weights, which also means uncertainty because you have limited data. So this part is basically denoting limited data uncertainty, and this is denoting the noise uncertainty. Remember, in the previous case we got beta inverse plus something like this. Where I say beta inverse was because of your data was having noise, so beta inverse is now replaced by Bn by An. And I also said that the second term was because of limited data, and if the data goes to infinite, it will go to 0. That is here. And same here also. If data goes to infinite, Vn will become 0, everything will become 0. The second term. Okay. Now this derivation is quite involved. Please do it. Otherwise, you will not understand. This is not something you will understand just by seeing or by just writing, taking notes. This you have to do or repeat by closing your notes and doing it yourself. And when you are getting stuck, look at the notes. You have to do it like that, only then this thing you will understand. Okay, because there are so many things here, so many things happening together. It is very easy to get confused. It is very easy to mix things here and there. It is very easy to take Vn as something else, V0 as something else. So please do the derivation. Obviously, you have to do the derivation because it's in homework. And that is the exact reason I also repeated it in the practical also. So this I have repeated in practical and homework so that you at least practice 2 times. Okay. You have to practice it, otherwise it will not work. Okay. So we are done with Bayesian linear regression. So next class we will start with sampling. Okay. And as we go to sampling, we will realize now the maths will reduce and concepts and intuition will come into picture. Okay. So maths was there because in this case you can do things analytically. In sampling, nothing can be done analytically. So in fact, you are sampling because you cannot do things analytically. So as a result, derivations will now reduce, and intuitions, understanding, all those things will come, because this was understanding plus derivation. So that will now reduce. Okay. Okay. So I think Monday is holiday, but after that 31st is a Saturday, which is a Monday routine. 7th is a Saturday, which is a Monday routine. So that means 31st is Sunday, so 29th. We are next meeting on 29th, which is next Thursday. Then we are meeting on 31st, then on 1st, then on 4th, and then on 7th, or then on 5th or 7th, something like that. Okay. So we will have continuous classes, I mean, up from starting next Thursday, but Monday is holiday. Okay. But again, one more thing is that start doing your homework. It will take time. You cannot do it in one night or even 2-3 nights. It's not possible. So start doing your homework. If you start now, you will not be under pressure. But if you try to do it on the last night, not possible. I'm telling you now only. Okay. Okay. Thank you.